Okay. I see it. I don't think you do. Hopefully you see it now. It's got nothing to do with your class. Oh, let's see. Go back a little bit. Okay, this looks like what we were doing last meeting time. It might have been in the office hour. Anyone recognize it? Was it office hour? I think it was. We went over problem 18.
Yeah, that looks like office hours.
Okay, so maybe I'll say a word about it just in case someone wasn't in office hours. I hope I did this in class. This was an intuitive argument of this theorem that if I is recurrent and I leads to J, where I and J are states in a Markov chain, then if I leads to J and I is recurrent and J is also recurrent, and these probabilities, the probability of eventually going from I to J and eventually going from J to I, are each 1. So there is a formal proof in the text. I went through this intuitive kind of idea where if at time 0 you were at I, then because it's recurrent, you're going to have to come back at some other times. So I listed those times N1, N2, and so forth. And then the fact that I leads to J means somewhere on this list, you actually get from I to J. And whenever that happens, then sometime thereafter, there's another I because you have probability 1 of returning from I to I. And then the whole thing starts again, which means J will be on the list somewhere down the line. And so you'll essentially be visiting J infinitely often with probability 1. And that's what the conclusion is. We talked a little bit about a Markov chain being irreducible. That means instead of having different equivalence classes like this picture shows, you could have everything communicating with everything else. So that means you can get from any state to any other state. This would be an example of that. On the other hand, this one, which was problem 19, I think was not an example of that. Okay, after that, as I've already said, we did problem 18 in the book. We have that. This is interesting because you have an infinite number of states. So this continues. There's only 2 kinds of one-step transitions. You either go up by 1 or you fall back all the way to 0. I didn't show all the arrows going back here, or maybe I did and they got erased, who knows. But there are catastrophe arrows going here all the way back to the 0 state. And each of those have probabilities 1 minus P. And that's how this thing looks as you keep on going and you keep going up by 1 or down all the way to 0. It's called a birth catastrophe chain. And what we showed, well, we showed that 0 was recurrent because we added up all of these things and they added up to, by a geometric series, to 1. So 0 is recurrent. But then 0 leads to 1. It's pretty clear. There's a positive chance of going from 0 to 1, that probability being P. So by the theorem that I just mentioned, that means 1 is recurrent, but then 1 leads to 2, so 2 is recurrent, etc. So that way you're able to show that all the states in this chain are recurrent, and that's what's meant by being a recurrent state. Okay, I think that was more or less what we did Friday. Any questions? We also set an exam date, which I'll just remind you of. So our first exam is not this week, but next week. And we chose Wednesday, the 29th, I believe, right? So exam 1. I'll be giving you reminders throughout the time. Was Wednesday. September 29. And I also gave you a sample test and asked you to start doing any of the problems that you could do. And we can talk about it if you want, since I'm talking about organizational things. You want to talk about a time to get together to review some of the stuff on the sample test? Good times. Well, there's always after class. So I'm happy to do a problem here and there in office hours on the sample test. But it might be a good idea to have a separate day or time set aside. Normally, I would recommend off university hour. That would be Tuesday or Thursday from noon to 1. But those times are filling up with me. I have committee work I'm doing, so I can't do those times. I am free on Tuesday, Thursday afternoons, sometime after 1. So if those days are good, let me know, or I'll take suggestions. I don't think it's key that we need to do it tomorrow, so that's a Tuesday. Probably by the end of the week, we should have, that'll give you more time to do these problems. So probably by Thursday or Friday, it would be nice if we can schedule it sometime on those 2 days. Any suggestions?
Is this like we're almost planning like another time to meet? Or is it okay?
Yeah,
It's
finding
not
another time to meet that's not class time and not office time. I mean, those times, there'll always be a little time in class to work problems, and there hopefully be a lot of time after class to work problems. But sometimes it's just good to have an hour and a half devoted to going over the sample test. So let me ask, what about Thursday afternoon? Because that's, as I say, a decent time for me. So for a review session, that it seems like that's giving you enough time to at least look at the test. I'm suggesting maybe Thursday, either at 2, 3, or 4. Those would be possible starting times.
3 or 4 would be ideal for me.
yeah, 3 would work for me as well.
Okay, so let me see. Let me stop sharing, just make sure who cannot come at 3 on this Thursday, who would like to come. Is there anyone who's left out? Candace, okay, and Hugo and Alejandro and Cassidy. Does 4 work better for you folks? Candace, no. Alejandro, no. Cassidy, no.
I have an exam and another class at 4 o'clock on Thursday.
On Thursday, so Thursday's not going to work for you. Yeah, and what about the rest?
I have class.
Yeah, same. I have an exam as well.
Okay, would it, well, you probably wouldn't help even to move it up because your mind is on the exam, right? So I don't blame you. Well, let me think of an alternative. The morning probably won't work as well. What about tomorrow? Is that better? I know it's
Same issue.
well, you don't have exams, do you? Or do you? You may have a class, but hopefully I took away the exam issue. Candace, not, no.
The only class I have on Wednesday is you, but I know you have the class in the afternoon.
Yeah, I could do, let me think what. What about Friday afternoon after, I know it's unpopular, but because it's unpopular, maybe it may be available. What about Friday at 5?
Like after class? Oh, at 5.
Well, after class, I'm here. I mean, the office hours aren't going away, okay? But I'm trying to find a dedicated time just to do the sample test. So what about 5 o'clock on Friday? I mean, I doubt.
That works.
Yeah, I doubt you have an exam that day. I mean, it's possible, but I doubt it.
This coming Friday is fine with me. I think the only other thing I have is your real analysis class.
Yeah, which is, I'm still leaving time for the office hour there. So it'll be a busy day for me, but okay. Is there anyone who can't do it Friday at 5? Who would like to do it? Okay, so we got a miserable, it's like, we got a miserable enough time that you all can make it. Okay, let's do that. Let's make it Friday at 5. So let me go back to the screen if I can. And if you can't make it, I'm sure there'll be students recording it, and I'm confident they'll share it with you for a fair price or something. I'm just joking, I hope. I hope they share it with you for nothing. So review, I think we've come down to Friday. This Friday, what is this Friday? I don't even know. Today's the 20th. So what is that? Is that right? Is it the 24th? Yeah, I guess so. I'm just trying to remember if I have anything going on then. I don't think so. 5 to maybe it's like 6:30 or 7, something like that. Why don't we say 7? Okay, so write it down, remind me next time. Well, actually more important to remind me and everyone on Friday. And it's just to go over the sample test. And the good thing about this time, it does give you more time to try to work some of the problems. Okay, let's get back to the math. Got this all good. Let's see, where are we? We're here. What's this? Oh, that's me trying to find a good time. Okay, so let me just add a page in here. Doing, I don't know. Okay, so I think I'm ready to go. So there's about 2 or 3 things we would like to take care of here in preparation for our exam next week. So I think I have to decide which to do. I think I'm going to do problem 9 is a little is useful. So let's go through problem 9 a bit and then show you how it's used. Okay, so we're looking at problem 9. So it's problem 9 on page 42. So part A says this. It says, well, it gives you tells you how. Use equation 29 to verify Part A, and part A says, if you know you started at state X, that's this notation, the subscript notation tells you where you're starting. The time it takes to first hit Y is less than or equal to n plus 1, can be expressed in terms of this equation. You can go from X to Y in one step, or, which means you add, you can go from X to some other place, Z, where Z is not equal to Y. And then from there, starting at Z, you can look at the time it takes to first hit Y and want it to be less than or equal to N. Okay, so, we're into week 5 here. And this is complicated looking, right? I mean, there's no way to say anything else. It's got X and Y and T's and N's and P's, and it's a complicated looking thing. I'm not saying it's impossible or anything like that, but I'm just saying first glance, it's understandable. At first glance, you look at this and you say, what? Where is this coming from? What does it mean? So let's back it up a little bit. They tell you how to proceed. They say use 29. So go look for equation 29. It's something we've done recently, I believe. So I will hunt for it. And I found it, equation 29. So the equations, of course, are numbered. And equation 29 is on page 15. So see page 15. And if you go there, you'll see at the bottom of the page this equation, which is number 29. And it says this. If you start at X, the time it takes to first hit Y is n plus 1 units. And n is thought of to be, some natural number. So this is a condition of probability because you're starting at state X and you're first hitting Y. I'm going with their notations. I often use I and J, but here I'm using X and Y, just following the book's notation. By this equation, it's equal to the sum for all Z not equal to Y of going from X to that Z. Probability of doing that times the probability of starting at Z at the first time you hit Y is equal to N. And as they say, N is 1 or bigger. Okay. Now, I think someone asked me to go over this in class because I remember doing 28. 28 is on the other page, page 14. And I think I went through this explanation. Of course, this is the kind of commentary by authors that drive students nuts. So it's humorous to refer to it. Right under equation 29, it says this formula is a consequence of 27, but it should also be directly obvious. Okay, so usually either that's a turnoff when someone tells you something's obvious and you have no idea, especially when it looks so complicated. To be told it's obvious could be a disappointment. Or I would take it more humorously. What's obvious to one person is not obvious to another frequently, and this might be one of those cases to you. But then, fortunately, the authors don't leave it at that. They go on to explain why they think it's obvious. So and I may have done that before, I don't recall, but let me at least do it now because it looks like it's a short way to get back into this topic. So it says, for in order to go from X to Y for the first time in n plus 1 steps, So that's the mindset. That's what's going on the left side. You're starting at X, and the first time you hit Y is n+1 steps later, because this is the first hitting time, right? Which means you weren't at Y earlier. So you're trying to find the probability, and if it helps, you could rewrite this way. We've certainly done this before. We can assume that at time 0, we're at X. So this is a conditional probability. And the time it takes to first hit Y is n+1 steps later. Think of n as being like 5 or 6. Don't think of it as being like 1 or something, because then it would just be, it would still make sense. It would say the first time you hit Y is time 2. So, I mean, it would make sense, but n doesn't have to be small. It could be, up further along. So you start at X, you want to first hit Y this many units times later. And then let's look what they say further. They say in order to go from X to Y for the first time in n+1 units, it's necessary to go somewhere after the first step. So again, think of n as somewhat large, like 5 or 6 maybe. And they're saying if you're trying to get from X to Y, you start at X and you're trying to get Y to Y the first time in this much time, where were you after 1 unit of time? Well, you went somewhere. Where? Z. That's what this is saying over here. And what is Z? We're assuming Z is not Y, because the first time you hit Y is later, which means after 1 unit of time, you went to somewhere other than Y. And the probability of that happening is this transition probability, the probability of going from X to Z in 1 step. Okay, so you're at X initially, you've gone to Z, which is a state other than Y after 1 step. And then what must happen? Well, now you can imagine that you're starting at Z, and the first time to hit Y is no longer n+1 because you've already used up one of the steps of travel. So the first time to hit Y would be n steps. And then this is summing over all the places you might have gone on that first step. So you could picture this as a tree. That's how I would think of it. I'm starting initially at X, and then I'm going somewhere other than Y. So those would be all the branches of where you could go. And then after that portion of the trip, then you have to go from Z, and you're not going to hit Y until n steps later because you've already used 1 step. And you're trying to find the probability of the time you finally get to Y is n+1 steps, so there's n steps left. And then summing over Y is like going through all the paths of the tree. Does that help?
It cleared it up for me a little bit.
Good. Yeah, it may not. Yeah, I like your adjective. It cleared it up is almost too much to hope for. I mean, I'm delighted if you feel that way. But if it clears it up, even 30, 40%, then it's the kind of thing you got to mull over a little bit, make sure you buy it. And you can easily construct an example. So you can construct an example, and then this might make more sense. But I'll say it one more time, and then I'm going to move on. This is saying, assuming that we're starting at X, the first time we hit Y is n+1 steps later. So what that must mean is after 1 step, you went to a state that's not Y. Because if you went to Y, this would defy hitting it in for the first time n+1 steps later. So you went to some state that was other than Y after 1 step. And then from there, you went from that step you're at, which is called Z now, to Y in n steps, because after n+1 steps, you're first at Y. So it must take that many steps to get to Y from Z. And then you just sum over all the places that you could be at, all the Z's that are not equal to Y. All right, let me hope that makes some sense of it. And they give an argument that's, pretty similar to what I just gave. If you need a little more, I'm happy to do that maybe after class. Okay, so I can easily do an example, but I think I'll avoid it just to try to get back to what I'm after. So with this in hand, we assume that 29 makes sense to us. Well, if 29 makes sense to us, what is that they're asking us to verify? This thing. Well, what's changed from here to here? What's changed is the first time we hit y here was n+1. The first time we hit y here doesn't have to be n+1. It has to be n+1. It has to be less than or equal to n+1. The first time you hit y has to be less than or equal to this. Okay, so let me see if I can sort of talk us through a proof of this as well. Yeah, so what we're trying to say here, this is the one we just went through. We're trying to say if there's an inequality here, all we have to do to embrace that inequality is to put an inequality here. And that's what's going on here. They're taking 29 and replacing the equality here by this inequality, and they're replacing the equality here by this inequality. Okay, so now let's reel out the argument I just gave for this and try it for this. Okay, so you're starting at x, and the first time you're hitting y is n+1 or less, which is a little different than before. Before we knew it was n+1, but it's n+1 or less. Okay. What's the smallest it could be? Well, maybe the first time you hit y was after one step, which means maybe you went from x to y in one step, and that's this. It's possible because then ty would be 1, right? Okay, so what we're doing now is conditioning upon how long it takes to hit y. If it takes to hit y for the first time one step, then we've gone straight from x to y, and that's the probability of that happening is this, the chance of going from x to y in one step. But maybe you didn't go from x to y in one step. Then where did you go on your first step? You went to z again, where z was not equal to y, just like down here. And the probability of doing that is pxz, the chance of going from x to z. And then once you're here, then what happens? The same argument that we had down here. Where are you coming from the next step? You're coming from z, because that's where you are after one step, where z is not equal to y. And then what's happening? Well, you've already used up one of your steps, so you still want to get to y in the remaining time, but you've used up one step, so this n+1 becomes n. And now the time to get there is not n+1, but less than or equal to n+1. So that's almost the same argument that we had here. And so what we're saying is, if we sum up of all the places we could be at, which are not y, and then we know where we went in the first step, and the chance of getting from that step to y in n or less steps would be what we multiply it, because when you do both of these things, you are going from x to y for the first time in what, n+1 steps. It takes you one step to go here. n+1 steps or less. And then the remaining steps would be n or less. So together, the total number of steps would be less than or equal to n+1, which is what this is saying. So the argument may sound like a little double talk, but it's more or less the argument we did here, replacing the equalities here by inequalities, which really says you're not necessarily waiting for the n+1 step to hit y. You could have hit y sometime at the n first step or sooner. And all you have to do in order to make this still hold is just make the inequality be over here, which allows the chance that you were first at y at time n or sooner, which is all this is saying. Okay, well, again, that may only make 30, 40, 50% sense. If it makes more sense, then I'm thrilled. But if it only makes 30, 40, 50% chance of understanding that, then think about it more, ask me about it more, ask me for an example. I'll give you one after class. Right now, I want to go with that argument. Okay, so that completes A. Now what's left? Let's go back to where this problem is. This problem is on page 42. The part that I really want to get to is B. So we've done A. Let's move down the page and do B. So what does B say? B says we want to show, so and it's understood, show or prove that the probability of going from X to Y eventually is equal to the probability of doing it in one step, or, which means add, all the ways you can go someplace other than Y. So we go to Z that's not equal to Y again. And then from there, so you go to that place. So you go from X to Z. And then from there, you've got to get back to Y eventually. So that would be the probability of starting at Z and ending back at Y eventually. Okay, so this is problem 9. So this is 9. This is what 9b is talking about. And they want you to believe this. Well, there's two ways to think of it. Again, you can do what he would call the interpretation. So let me do the interpretation, though. I pretty much did it when I wrote it out. You're trying to find the probability of starting at X and eventually getting yourself to Y. And eventually means if you take an infinite number of steps, right? Or actually not, because what is this thing? This thing is what? It's the probability, if you want to remember what this is, that at time 0, you're at X. And the time it takes to first get to Y is what? Less than infinity. And we've talked about this before. That means the probability that you first hit Y could be 1, could be 2, could be 3, any finite number. And we're interpreting that as the probability of starting at X and eventually working our way to Y. Now, what is this doing? This is breaking it up into, okay, if you're going to start at X and you're going to end up at Y eventually, maybe you did it in one step. That would be the easiest thing, right? That would be the probability of going from X to Y in one step. That's the one-step transition probability. So maybe you went straight from X to Y in one step. If you do that, then the first hitting time would be 1, right? Because you actually first hit Y in one step, and that would satisfy this thing. But maybe you didn't do it in one step. If you didn't do it in one step, you had to go somewhere from X where you went again, called Z. And Z is a state, but it's not equal to Y, because we already treated that case. If you went from X to Y in one step, that was dealt with here. So you actually took a step from X to some other state other than Y, because we already dealt with going there directly. Okay, so you've gone somewhere else after one step. And now what has to happen for you to eventually get to Y? You have to, from that place, eventually get to Y, which would be rho ZY. So think of this sort of as a two-step process. If you didn't go from X to Y in one step, you went from X to some other state Z, then Y, Z is different than Y in one step. And then from there, you eventually you figure out the probability of eventually getting from Z to Y from Z. So this would be like a multiplication rule. If you're going to go from X to Y eventually, and you don't go directly to Y, you went somewhere else. And then from that somewhere else, you eventually have to find yourself back to Y. And those are all the cases. So this is like a multiplication of getting from X to Z in one step and getting from Z to Y in all the other remaining possible steps. Okay, that's an explanation of this. A different explanation would be take what we just found here. So we did part A already, and this sounds very similar to that. The difference here is you're actually going from Z to Y in a finite number of steps. Here you're going eventually, so it could be arbitrarily big. So a different way to get from this equation, which we did in part A, to the one they're asking us to show in part B, is to take the limit of both sides. So if you were to take the limit of this side of it, and here's an assumption we'll make. We'll say taking the limit as n gets large in here, we can bring it inside the parentheses and just take the limit of this quantity as n gets large. So if we take the limit as n gets large of this side of the equation, this part of it becomes infinity plus 1. So that means this becomes infinity. And if you do to both sides of the equation, you're taking the limit as n gets large here, this becomes infinity. And this would be the only place where it occurs is here, so this would be infinity as well. Okay, so now that says the time it takes to first hit y is less than or equal to infinity. But we've already defined this thing over here to be this, right? So this is beginning to look like the definition of rho xy. The only difference is perhaps here you can let ty be infinite. And what would that mean? That would mean it takes you, that means if you have an infinite amount of time, you could actually get to y. But I'm going to say that we're in a finite state space, so that doesn't really apply to us. So what I'm suggesting is that when you take the limit of this as n gets large, this left side becomes this, because it starts to look very much like this. Similarly, this part of the equation of part A starts to look like rho zy, and that's a different way of getting the whole thing. Okay, well, now that we've gone through it, two things I want to finish up on. One, I'd like to be able to remember it without going through the whole proof. So I'm sort of going to go through the first walkthrough proof that I gave of this. This says if you're going to go from x to y eventually, you're trying to find the probability of getting from x to y eventually, which means you're letting time go off to infinity. You either get there immediately in one step, or you go somewhere else in one step, and then from there you eventually get from that point, that state, to where you're headed y eventually. So this looks like a sum rule, because you either get there in one step or you don't. It's going to take you more than one. And if it takes you more than one step, then from wherever you were after one step, eventually you have to be able to get to where you want to go, which is y in the remaining steps, and that's what this is. Okay, well, that's my hope for understanding this formula and remembering it. Let's do an example. This turns out, so I'll just tell you, this turns out to be a different way to calculate the rows, rho xy. So let me give it a simple example if I can. example. So how about 0 and 1 going back and forth there? And from 1 you can get to 2. Loop here. Get the 3. Make it a little more interesting. Okay, suppose the one state transition probability diagram looks like that. Let me see if that's going to be what I. Yeah, I'm trying to decide if this is where I want to leave it or if I want to make another way to get to 3.
Professor, don't you have to have 3 go somewhere as well?
Yeah, 3 will, at this point, 3 will just be going back to itself.
Okay.
Um, let me think about this. Okay, so suppose we have these kind of diagrams. Let me put some numbers in. So maybe this is a half. And this is a half, and then that's 1. And now call this a third, and this 2/3. And maybe this is a half. This is a half, and this is 1. And now we have to worry about this. So I don't know. Two fourths and 1/4. Okay. Let me see. Now, when you make a diagram like this, you got to make sure that from every state, the probabilities add up to 1. So here's a third and 2/3. That looks good. Here's a half and 1/2. That looks good. Here's a half and a half, that looks good. Here's one, that looks good. And from here, 1/4 or 3/4. Yeah, so everything adds up to one. If we wanted to make a state, if we wanted to make the diagram for it, we should be able to do it pretty quickly. Let's do that. So from 0 back to itself is not possible. From 0 to 1 is 1/3 probability. From 0 to 2 is not possible. From 0 to 3 is not possible. From 0 to 4 has a 2/3 chance. What am I making? I'm making the one-step transition probability matrix in the diagram. Let's continue. From 1, you can go to 0 with probability 1/2. From 1, you can't go to 1, but you could go to 2 with probability 1/2, and that's everything. So the rest must be zeros. From 2, where are you going? You can't go to 0 in one step, nor can you go to 1. You could go back to 2. You could go to 3. That's a half, sorry. And then from 4, I'm sorry, where are we going? From 2 to 4 can't be done. Okay, oh, no, I lost something here. From 2 back to here. 2 to 0 can't be done, 2 to 1 can't be done. Oh no, I'm in 1. So from here, I either go here. But look, it has to add up, so it has to be 0. Okay. All right, almost done. 3. Here at 3, you only go back to 3. And if you're at 4, you either go back to 4, which has a probability. Let me see, from 4. Oh, you can go to 3, which has a probability of 1/4, or you go back to 4, which is 3/4. Okay. Is everyone okay and able to go from the diagram to the matrix? I hope so. This should be a stochastic matrix. The row should add up to 1, and it is. Okay. Can we classify states? Well, it's pretty clear that 3 is recurrent, because if you're 3, you're absorbed, you never go out, so the probability of returning to 3 would be 1. So 3 is recurrent. What about 0? Well, there's a chance that you go from 0 to 3, which means, and then you'll never come back. So that's transient. Well, because 0 is not the only transient state. All these states are transient. Why? Because from wherever you start, there's a way to get to 3. And once you get to 3, you have a positive probability of never getting back, right? So 0, 1, 2, and 3 are all transient. So here. Questions thus far? Okay.
That should be 0, 1, 2, and 4 are transient, right?
Oh, you're right. The 3 I already said is recurrent. Thank you. Thanks for the correction. Is it okay now?
Yeah, it is.
Okay. So now I want to get to the point at hand. I would like to find row XY. Now, what we know, well, 0 is recurrent. So we know that 0, 3. Row 3, 3 is 1. If you start at 3, you end up there. So we know that. And we also know more, because row 3, 0 would be 0. Row 3, anything would be 0, right? Why? Because if you're at 3, you're absorbed, so you're never going to get anywhere else. So the probability of starting here and ending up at any of these states is zip. It's 3 to 0, 3 to 1, 3 to 2, 3 to 3 is 1, and 3 to 4 can't happen either. Okay, so there are some rows I just know from the way the picture looks. Everyone follow me? Since this is recurrent, being recurrent means the chance of going from 3 to 3 is 1, and that's pretty clear from here. It's an absorbing state will always be recurrent. And not only that, an absorbing state, from an absorbing state, you are unable to go anywhere else. So these rows will be 0. But what is not known is some of the other rows, right? Let's see. Okay, do we know any of the other rows? Just by the diagram, okay. So, yeah, if we start at 2, what's the probability you'll end up at 3? Well, that's for sure, right? Because the only way not to, from 2, the only place you can go is 3 other than itself. And if you tried to stay here forever, that would be like taking 1/2 to the nth power. And the chance of that will be essentially 0. So what I'm suggesting is row 2, 3, from the way it looks, row 2, 3 should be what? For sure. If you really wanted to, you could figure that out from definition, because it would be the sum of, well, it's not hard. Maybe we can do it. That's not my main point. This would be the probability of starting at what? 2. And the first time you get to 3. So T3 is less than infinity, right? So you could do it for the first time right off the bat. So that'd be a 1/2 probability. The first time you hit 3 is 1 unit, and that's 1/2. Or you could loop once and then go over. So that's a 1/4. Or you can loop twice and then go over. That's an 1/8. And you get a geometric series that adds up to 1. So that's where that comes from, if you need a little more explanation. So from 2 to 3 is certain. And from 2 to anywhere else is 0, right? You can't get from 2 to 1, nor 2 to 0, nor 2 to 4. There's no way. The only way you can get anywhere from 2 is either stay at 2 sometime and then go over here. So that tells us, okay, that's giving us all the row 2 anywhere else is equal to 0. When what? When anywhere else could be 0, 1, 4. Okay. What about row 2 to 2? Okay. So what about this one? That would say if you start at 2, what's the chance eventually you get back there? Well, that really means this. So let's write it out. If you start at initially at time 0 being at 2, and you want to get back to 2 for the first time in finite number of steps, the only way you can get from 2 back to 2 in a finite number of steps is to loop once. Because if you loop twice, then you're not getting to 2 in 2 steps, because you've already been there on the first step. So what am I suggesting? This thing just becomes this. The probability of getting to 2 in 1 step, given that you started at 2. And that means you looped, and that's 1/2. And that's it. Because you can't get from 2 back to 2 for the first time in 2 steps. Why? The only way to get back is to loop, and in 2 steps, you would have gotten there already in 1 step. So, okay, so we finally have our first non-zero or 1 row. This one is 1/2. Okay, so what have we done? How many rows are there? Okay, well, this could be any of 5 states. And this could be any of 5 states. So there would be 25 of these guys, right? 25 different ways or different rows. But we've already done the ones when you begin at 3, that these 5 are done. And we just took care of the ones when you began at 2. So when you began at 2, 2 to 3 was 1, but 2 anywhere else was 0, except for 2, and 2 to 2 was 1/2. So we've done 10 of the 25. We did the ones that began with 3 when x was 3. We did the ones that began when x is 2. What we haven't done are the ones when we start at one of these guys. Okay, so that's what's left. So we want what's left. So I was trying to come up with an easy problem, but I came up with a pretty, it's not hard, it's just sort of a lot of work so far. What's left is to find row x, y for what? For x equal 0, 1, or 4. But we've already said that these are all transient states. And so is this. So if we start at any of these states, eventually we have to end up where? At 3? There's nowhere else to go because these are all transient states. Did I identify that? I hope. Let's see. Yeah, over here. 0, 1, 2, and 4 are all transient states. So if you start at any of these transient states, the chance of getting to 3 will always be 1, because eventually you're going to end up over here and you're going to get absorbed. Okay, so that's how many more? What's left is this for this, but I'm saying if you're picking y to be, if you pick y to be, I can't remember what my state is for y, 3. My absorbing state is 3. Then I'm saying row 0, 3 is 1, and row 1, 3 is 1. And what else? Row 2, 3 is 1. And I think I've already done row, well, I guess this one I already did. 0, 1, what's 4? Oh, what's the other one? 4. Okay, these guys I haven't done before. This one I have done before. So there were 25 altogether. I've done 10 and 3 more, I've done 13. So roughly half of the rows are figured out and half of them are not. Okay, so what I'd like to do is, so we'd like to figure out the remaining rows are those that start at either 0, 1, and 4 and actually end up, well, the harder ones, the ones that start at 0, 1, and 4, where did they end up? We know row is less than 1 for each of those because they're transient. So here would be a question. We want to find the rest of the rows. Now there's 2 ways. You could again use the definition, but let me get to the main point here. Let's use problem 9. So what did problem 9 say? Problem 9b in particular. 9b says, if you want to get from x to y eventually, you either do it in one step or you go somewhere else. So you've gone from X to Z. And from there, you get from Z to Y eventually, and you're summing up over all the Z's not equal to Y. Okay, so what is the chance of going from 0 back to itself eventually? I actually think we could do that without this problem 9b, but I want to use problem 9b so you see what it's about. So let's see what it says. It says row 1, 1. I'm letting X and Y be 1 here. Will be the probability of going from 1 back to itself in one step, plus the probability of going from 1 to somewhere else, and then from that somewhere else back to 1. So I'm letting X and Y be 1 in problem 9b. If we do that, we get this equation. Let's write this out a little more. The chance of going from 1 to 1 would be the probability of going from 1 to 1 in one step. Is there such a probability? No. You can't go from 1 to 1. Yeah, you can't go to 1 to 1 in one step. That would correspond to having a loop here, and there is no loop. So the first term is gone. So where can you go from 1 in one step without it being 1? Okay, in one step, you can either go to 0 with probability 1/2, and the chance of doing that is that. So that would be Z equals 0, and then you'd have to be going from 0 to 1. Or where else can you go from 1 in one step? You either go to 0 in one step, or you go to 2 in one step, and that has probability 1/2 as well. And then from 2 to where? Back to 1, right? Okay, so this is using 9b to figure out row 1, 1. Now, some of this we already know. The chance of going from 2 to 1 eventually is 0. From 2, you can't get to 1. You can only get absorbed. So row 2, 1, we already knew is 0. So this term here is 0, which means the whole thing is gone. And row 1, 1 is 1/2 the probability of row 0, 1. Do we know row 0, 1? No, we don't know that. But now we know this much. Row 1, 1 is 1/2 of row 0, 1. So we have one equation and 2 unknowns. Let's see if we can find another equation. This is what we were trying to find. It led us to this one. So let's use 9b on this one. Again, using 9b, we can say the row going from 0 to 1 would be, how would 9b work? Well, this time X would be 0 and Y would be 1. So you would be going from 0 to 1 in one step. Go back to the diagram. 0 to 1 in one step is a third. So this term here, in this case, works out to be a third. Plus, instead of going from 0 to 1, you can go 0 to some other places. Okay, so where can you go from 0 in one step? You go from 0 to 1. You can't go from 0 to 2, not in one step. You can't go from 0 to 3 in one step. but you could go from 0 to 4. And the probability of that is 2/3. So that would be in here, 0 to, what did I say, 4 with probability 2/3. And then you'd have to multiply that by the chance of going from 4 to where? 1 eventually, which is what this is saying. Okay. So I've used 9b twice. I've used it once to get this boxed equation, and now I have a second boxed equation. So unfortunately, I don't know row 1, 1 yet, and I don't know row 0, 1 yet. What about row 4, 1? Do we know that? Row 4, 1 is going from here to here. What's the chance of starting at 4 and eventually ending up at 1? 0. Why? Because there's no way to get from 4 to 1. There's no arrow going back up that way, which means this is useful. So that means this one is 0, which means we now know row 0, 1. That's 1/3. And since we know row 0, 1, we can multiply it by half and get row 1, 1. Which would be a half times a third or a sixth. And my point is made. What's the point? The point is problem 9b gets you linear equations in these rows. And if you write out enough of them, you should be able to solve the equations. I don't know how many equations you have. This case, you have 2 equations and 3 unknowns. Row 1, 1, row 0, 1, and row 4, 1. But fortunately, looking at the diagram, this one was 0. So now you have 2 equations and 2 unknowns, and you can solve it. This gives us a different way to figuring out rows without having to use, all the different paths. Well, I've run out of time, but I haven't run out of the problem. So I'll let you finish it up. Homework. Finish this problem. If you want, I'll do it right after class. Don't forget you have the sample test to do as a problem as well. So the main point of today is what? We proved 9A and B, and we're actually looking at B as useful. What is it used for? It's used to find the rows by getting linear systems of equations. When I said I leave this to finish, somewhere I think I'd already said we did 13 of these. And now maybe I've done 2 more, so 15. But there were like, what, 25 altogether? So we haven't found all the rows. So this problem is sort of a lot of busy work because there are, what, 5 states. And what makes it hard, if all the states were recurrent, then it would be easy. Because all the row i's would be 0 and everything leads to everything else. And everything would be 1. But when you have transient states, as I thought up in this example, some of the rows are no longer 1. Well, I guess we already have this one. Row 2, 2 is a half. But now we've seen row 0, 1 and row 1, 1 is aren't ones either. Questions? Okay. So I'm done with today's lesson. Let me see if there's oh, well, this should help you. Do problems 19 and 20. Well, particularly 19. If you were having troubles doing 19b or maybe 20, well, okay, 20 doesn't ask you to do that. 20 asks you for something else. But we do now have a different way to do 19b. Any questions? Okay, I'm going to take my water break. I'll come back and go to office hours and talk about whatever request you might have or clarifications. Let's see. Beecher still here. Is Zach still here? Yeah. Zach, are you there? Yes, he may not be there. Okay, can't tell. So let me see who's really here. Yeah, I should take roll after this. Candace, you're probably here. Are you still here?
Yes, I'm here.
Yeah, okay, thank you. Beecher, are you still with me?
Yep.
Okay, Ricky,
Yeah, I'm still here.
Raymond,
Yep, I'm here.
okay, cool. Zach, are you here? Okay, that's the guy I wanted to talk to. So certain the guy I wanted to talk to, I can't get to. Okay. Millie, you're here, I assume, I hope.
Yeah, I'm still here, Professor.
It's good for me to do this because I could be talking to myself without realizing it. If you're all just taping it and you're off doing something else or recording it. Okay, but no Zach. So I'll talk to Zach another time. All right, any requests, any questions? It could be sample test, it could be stuff we did in class today, in the past, whatever.
I had 2 questions, Professor.
Sure.
The first, I was wondering if we could go over the, I guess the problem that's similar to this on the practice exam, because I tried going over it, but I'm a little confused just because there's, I guess, multiple. I mean, I guess what we did today would probably be a little easier, but
Which one is it?
I think it's the first one.
Okay, so number 1.
And then the other one I wasn't asked too about was you wanted us to restate the Chapman-Kolmogorov like equation, or like the
Yeah,
or like prove it. Can you like when you mean by like stated, do you want us to just write down the equation then and then I'm a little confused by like how much of like the proof you want us to do, or like what exactly you want it, what's like it's expected of the proof.
sure. So yeah, so it's the Chapman Kolmogorov equation. Yeah, okay. Let me see if I can put my fingers on the sample test, because then I've got what I need to talk about. Okay. Otherwise. All right, so not so quickly, hang on. No, naturally. So I'm finding everything but what I want. Give me a second here. Mhm. Well, okay. I don't find it, but you have it. So why don't I just have you tell me how the diagram looks? By the way, were there any other requests before I go off on these 2? If there are others, sure, it's a good time to let me know.
I also, oh,
Professor, I heard you asked for me. Sorry, I walked away from my computer.
Okay. Zach, I just added you to a co-author of one of our to our presentation. I want to make sure you're okay with that.
Oh,
It doesn't mean you're doing anything. Okay.
yeah.
what it means is you've been attending enough of those meetings in the past that I think it's I felt comfortable adding you to the co-author list. You're like one of 7 or 8.
Okay.
I can tell you more later what it's about, but it's a good thing, I think, because it could go down on a resume as something that's useful.
Yeah, that sounds great. Thank you. I didn't think I did enough to deserve that, but
Well, you didn't do, yeah, okay, so I understand what you're saying. You attended a lot of meetings. And so I don't have you as the speaker, and I don't have you as, you know, there are people on the list who've done more, but that's fine. You've been there enough, and so I hope this gives you some more impetus to do more. But
okay, yeah,
we could talk about it. We haven't been meeting lately anyway. So what I'm talking with Zach has to do about a research group meeting, a research group that I typically have been meeting with people, but I haven't been doing it the last several weeks because I've been busy with other things. And one of the things I just finished doing is putting together a proposal for a talk at a professional meeting for our research group members. And so I'm giving Zach some good and scary news, right? Good news to be on the list. Scary if I want you to do something. At this point, I'm not asking you to do much more than you've been doing. So don't worry about it.
okay, thank you. Yeah,
Yeah.
appreciate it.
And if there are others here who are interested in the research group, and I think there may be a couple who asked me about it in the past. The reason I haven't invited anyone of that description to it is we really haven't been meeting. But when we do, I will invite. I think Raymond, you're one.
Yeah, I wanted to double check about that. If I was on the list for that still.
You're in my mind. We just haven't been.
Okay.
We haven't been either. Either we've been meeting with a special objective, which would not be a good entry point for someone new, or we haven't been meeting much at all. So it's one of the two. But yeah, no, I haven't forgotten about you. I don't remember if there's anyone else who's here today who also expressed interest. Feel free to remind me if there is.
I'm interested. Professor Krennic.
Yeah.
Sorry, it's me, Millie. Is
Yeah.
that what is that again? Can I join?
Yes.
Can I
Yes.
join the party?
Yeah. We haven't been meeting much, so there's not been much of a party lately. But yes, remind me in another. No, I don't know. Just remind me in a week or two that it's about the research group. So the research group deals largely with what we're doing in here, and I really should bring this up in class for everybody. But for the moment, since it's the topic has come up, we deal with Markov chains, but we go further than than what's been done in this class so far. But if you're in here now for we're in week 5. So you already have enough to really at least understand what we're doing. And if you're interested, you're more than welcome. And that's a general invitation. The problem is we just haven't been meeting lately, but we'll resume.
Yeah, I would love to know more about that because I've been trying to find a professor to at least do some kind of research or something like that.
That's what we do. So we do research on sort of offbeat problems, things that we don't have time or energy to do in class, like a class like this. That's a natural thing that we do in the research group. So sure, Millie, I'd be happy to have you come to some.
Thank you. I asked one professor, but he kind of made it seem like it was too late for me and maybe all the professors were busy. So I'm glad that you kind of talked about it right here. I had to jump onto the opportunity. I'm sorry, even if it's just informational.
Yeah, no, I actually feel bad that I haven't brought it up to the general class. And I think the only real excuse for not doing that is that we haven't been meeting that regularly. So it's not like you've been missing anything. But yes, I have a research group, which I've been involved with for many years now. David Beecher, who may still be here if I look for him. Yes. Is he here? I don't know, maybe. Yeah, he's here.
I am. It was just difficult to drag up the window and unmute my mic again.
Yeah, it's okay. Anyway, David Beecher has been on, he's been a member of this research group for, I'm guessing, over a year now, right? Maybe more. How long, Beecher?
I started in January of 2020.
Wow, okay. Yeah, so he can, he's a good guy to talk to, and I'm sorry to give you conversations on this, but he really is. He's very knowledgeable. He's been there from the beginning and worked himself up where he's actually given talks at meetings for us. And so that's he would be very knowledgeable about what we do, but I'll also be happy to share with you what we do when I have time to meet with that group. Anyway, all right. So were there any other requests for the problems to do? I got these two.
Yeah, I also wanted to ask if you can go over the Chapman-Kolmogorov equation.
Yeah. So that's more
Yeah.
problems to do again, right? Okay. So that's fine. So let me turn the page. Can somebody give me the diagram for example 1 to spare me from having to go look for it? So, and it should be, how many states are there? Start with that.
There are 6 states.
Yeah, I thought so. Okay, so it's going to be a little complicated, but that's okay. 6 states, 0 through 5, are they?
Yes.
How are they arranged, in a circle or in a linear way?
You have the first 3 on top and then the next 3 below.
So 0, 1, and 2, and then 3, 4, and 5.
Yes.
Okay, tell me all arrows emanating off of 0.
From 0 to 1 it's 0.6. And then from 0 to 4 is 0.4.
Okay, and 1.
And then 1 goes to 1, 0.3. And then 1 goes to 0, 0.6. And 1 goes to 2.1.
Thank you. And 2.
2 goes to 2, 0.2. 2 goes to 3.6. And 2 goes to 5.2.
Thank you. 3.
3 goes to 3.4. And 3 goes to 4.6.
And 4.
4 goes to 3.5. And I think I am missing an arrow.
Okay, it sounds funny. Yeah, I did not accuse you of missing an arrow.
I'm looking and I'm like, I don't see another arrow. Here, let me.
Yeah, because 4 has to have another arrow because it has to add up to 1, and we haven't even got to 5, right? So someone can help them out. Someone else have the sample test. I hope I'm not missing the arrow on the sample test. If so, then it's a flawed problem.
Is this problem 1 on the sample test?
Yes.
There's an arrow that goes from 3 to 2, that's 0.3. Or I mean, from 5 to 2, that's 0.3.
4 goes to 4.5, Professor.
Okay, hang on. 5 to 2 was 0.3. Is that what I heard?
Yes.
Okay, and then what was the other one? I'm sorry.
4 goes to 4.5.
4 goes to 4.5. So there's a loop.
Yes.
Okay, and where does
And
5 go?
and then 5 goes to 5.4.
5 goes back to 5 with a 0.4. Okay,
And 5 goes to 4.3.
okay. This was a bad problem not to find. Sorry about that. But anyway, hey, it creates interaction. Okay, well, what else?
I think that's all of them.
Okay, so we could easily check. All the arrows from each state should add up to 1. So this does, this one does, This one does 3, 4. What about 3? 3 goes back to itself, 0.4. 3 goes to 4. That doesn't, I think that the numbers I got maybe wrong. So 3 goes to back to 3.4, is that correct?
Yes.
And does 3 go to 4.5, or is that wrong?
No, 3 goes to 4.6. You have the bottom arrow.
Oh, 0.6, okay. And then that's fine. Okay, so I think we're okay. And for 4, yeah, I messed myself up because usually I have these arrows on the bottom going from right to left instead of left to right. But anyway, it's all fine. 4 goes to itself, 0.5, and 4 goes where else? Back to 3.5, and then this adds up to 3.2. Yeah, okay, looks all fine. Okay, what is it, what we want to do? What do they ask for?
It asks us to state which states are transient and recurrent.
Okay,
And then part B was asking for a row of 2, 5, 0, 5, and 1, 5.
2, 5, 0, 5, and 1, 5.
Yes.
Cool, got it. Thanks. Okay, so this is one on the sample test. Keep an eye on it. So I'm doing this on OneNote. Sometimes the arrows and things disappear, but for the moment, let's see. Well, why don't I have you help me? Do you see a transient state?
I have 0, 1, 2, and 5 are transient, and 3 and 4 were reoccurrent.
0 looks transient because the two arrows leaving, there's no way to get them, right? So I agree with 0 being transient. What was your other one that you said was transient?
1.
Okay, 1, you can leave, but you can come back. So why do you think 1 is transient? Oh, because you can leave and never come back. Is that
Yeah,
right?
because at some point, since they all lead to 4 and
Yeah.
3, and it seems that 4 and 3 are reoccurrent. So once they're there, you're never leaving.
Yeah, and you can see it from here. If you're at 1, you might be able to go to 0 or 2, and once you do that, there's no way back to these guys. Well, you can get back to 2, but you can't get back to 1. Okay, so 0 and 1 do look transient. What was the other one you thought was transient?
2.
2. Well, okay, if you're starting at 2, you can go and then you can come back, but you could also go and never come back. So you're right. It looks like as long as you can leave a state and never get back with a positive probability, then it's transient. So it looks like 0, 1, and 2 are transient. I agree with that analysis. What about 5? 5 can go here and then you never get back to 5 as well, right? So these 4 were transient, which only leaves the other 2 as recurrent. And I think they are. Let's see. So what'd you get? 3 and 4 is recurrent?
Yes.
I think that's all fine. Does that, before we go further, does anyone have a question about any of those circled classifications? So I've classified 0, 1, 2, and 5 as transient. You could say it either way, transient or transient, doesn't matter. And 3 and 4 is recurrent. If you have any questions about any of those, let me know. Okay, then we just progress to the next part. So the next part is to find these guys, right? So 2 to 5 is interesting because there's a chance you'll go here, but there's also a chance you go over here. So it looks like this will not be, it will not be 1. Okay, and 0 to 5, let's see if any of these are easy. 0 to 5, there's a probability of that happening as well, but it's not clear what it would be. And 1 to 5 is similar to this. Okay, so Yeah, so let's use our problem 9B technique as a method of solving systems of equations. Let's just go for 2 to 5. Since we're interested in 2 to 5. Problem 9B says you can go, the chance of eventually getting from 2 to 5 would be the probability of going there directly, which would just be what, 0.2? Plus the probability of going from 2 to somewhere other than 5 to other than 5, oops, except that's not rho, that's P. So I've got it's the probability of going from 2 to 2 to Z. And then rho Z 5. And Z is what? Not equal. Not equal to what? 5. So I'm using problem 9B. And the chance of going from 2 to 5 directly is this. Now, where can we go? We can go, well, we can go back to 2, we can go to 3, or we can go to 5. But if we go to 3, then the chance of going from 3 to 5 will be 0. Because you can't, well, yeah, you can't get to 5 once you're in 3 and 4. So what this really becomes is the chance of going from 2 to 5, and it's 0.2. You can do it directly. Or you can, the only other place you can go that's not 5 that actually gives you something would be 2 again, right? So you could go from 2 to 2. 2 to 2 would have probability 0.2. And then from there, you still want to go from 2 to 5 again, right? So this is the first equation, and that should give you the answer. That should give you the answer for 2 to 5, because if you collect the row 2, 5 terms, you bring this to the other side, you have what? 0.8 row 2, 5 would be equal to 0.2. So row 2, 5 would be what? 0.2 divided by 0.8, which would be 1/4. Hopefully I've done that right. It looks pretty straightforward. So the thing we have to make sure we buy, if we're at 2, we want to go to all places not equal to 5. If we go, well, we can't get to these places, so we can forget about those. So from 2, the only 3 places you can go are straight to 5, back to 2, or over to 3. But if you go over to 3, which you could do, then you can't get from 3 to 5 because there's no way to do that. So that part is gone. And so it just turns out to be this. Does that make sense?
Professor?
Yes, question?
Yes, where'd that 0.8 come from?
Good question.
You subtracted the 0.2, right?
Yeah, I collected them. I brought this to the other side of the equation. So I have row 2 to 5 minus 0.2 row 2 to 5 equals 0.2. I just swung this to the other side of the equation and just think of this as a variable. So if you want, you could factor out the row 2, 5, and then you'd have 1 minus 0.2. And there's the 0.8. And then I just divided both sides by 0.8 over here. So basically I have one equation and one unknown. And that unknown is this guy. If you want to call it X, that's fine. And then it would be x equals 0.2 plus 0.2x, right? That would be the equation you just saw for x. You see what I'm doing?
Yes, thank you.
You're welcome. Okay, so we got this guy. If I didn't use this, then I'd probably have to start messing with the geometric series here. Should turn out to be the same. So now we have more than one way to do these. We've got the definition, and now we've got problem 9b. Let's go for row 05. Row 05. We want to know the chance of starting here of eventually ending up here. Well, again, why don't what? Let me see. Yeah, I don't think I'd want to do it by definition. I think I'd want to do it by problem 9b. So let's do that. So if I want row 05, let's go directly for it. 9b says there's a chance of getting from 0 to 5 in one step, plus all the chances of going from 0 to someplace z, where z is not equal to 5, and then going from that z the rest of the way to 5. So this is problem 9b. I'm using that. Okay, so, but some of these will not be possible. So, okay, let me write them all out, and then we'll go back and figure out which ones are possible. The chance of going from 0 to 5 directly, that can't happen, right? There's no arrow going straight from here to here. So that one's, so the first term here is 0. Now, what are the other ones? Well, maybe you went from 0 to 1, and then went from 1 to 5. Or maybe you went from 0 to 2, and then went from 2 to 5. Or maybe you went from 0 to 3, and then from 3 to 5. Or 0 to 4, and 4 to 5. Let me see. So I've either, but I got to go to some place that's not z, because I've already taken care of that one, and that one is 0. So I've either gone to 1 or 2 or 3 or 4. So this is what's left of this stuff. And now let's look and see what everything is. Hopefully some of these can't happen. So going from 4 to 5 can't happen. If you're over here, there's no way to get to 5. There's just no arrow back to 5. There's no path back to 5. So that means this term is 0. What about 3 to 5? Same deal, right? If you're at 3, there's no way to get back to 5. So that's good. That means this equation is getting simpler by the moment. Okay, so what we want is on the left side, 0 to 5. And what we have are two terms. But one of the terms here is what we just figured out. Row 25 was 1/4. So this one is relevant for this. Maybe. Why do I say maybe? Because row 25 is definitely 1/4, but what about P02? Is there a way to get to 0 to 2? No, not in one step. The probability of getting from 0 to 2 would be 0. So that means this is 0, 2. I thought it was going to need what we just did, but apparently not. Okay, now what about this? Can we get from 0 to 1? Yes. The chance of getting from 0 to 1 in one step is 0.6. So the equation we're getting from this is the chance of getting from 0 to 5 is 0.6 times the probability of getting from 1 to 5. Let me come up for air. Does everyone see what I'm doing here? they asked me for this. I'm using 9b, which is this. And if you write it all out, it's this. But then if you keep an eye on the diagram, these two were no can do. And this one, no can do for a different reason. Here, there was no way to get from 3 to 5 or 4 to 5 eventually, just from the diagram. But this one, the chance of getting from 0 to 2 in one step was 0 because there was no arrow directly from here to here. So that means 3 of these terms are 0. So the equation, this equation boils down to this. Now let's examine whether 1 to 5 is possible. 1 to 5 can happen, sure. Okay, so we have one equation and 2 unknowns, which is not useful unless I know I need another equation involving these two. So since this equation involved 0, 1, and I'd like to know something involving 1, 5, so I'm going to write down 9b for 1, 5. So 1, 5. It would still look like this, but now I have the probability of going, instead of 0, 5, it would be 1, 5. Plus what? Where you could have gone, again, replace zeros by 1, and then all the places you can go that are not 5. So you can go 1 to 5, you can go from 1 to 1, I suppose, and then get back from 1 to 5. Or you can go 1 to 2. What happened to 0? I don't know what happened to 0. I probably should have done that first. You go from 1 to 0, and then go from 0 to 5, right? But you could have gone from 1 to 1. In one step, and then go from 1 to 5. Or you can go from 1 to 2, and then from 2 to 5. Or where? 1 to 3. And then from 3 to 5. And then what? 1 to 4. 4 to 5. And going from 1 to 5, we already considered here. Okay, so this is how 9b looks for when we start with 1, 5 over here. You either go 1 to 5 directly, or you go 1 to 0, 1 to 1, 1 to 2, 1 to 3, 1 to 4, and then you multiply it by the chance of getting from this state to where you're trying to go eventually. Okay, so this is a little discouraging because it has a lot of other unknowns, but hopefully most of these go away. We'll see. The chance of getting from 4 to 5, I think we already said that's not possible. From 4, there's no way to get to 5 because these two states, you're stuck at those. The 4 to 5 is 0, so that term is gone. 3 to 5 is also 0 for the same reasoning. We went through that. We went through the exact thing, but from 3 to 5, you can't do. So that's gone as well. Let's see, can you go from 1 to 2? Yeah, you can. Okay, so you can go from 1 to 2. And can you go from 2 to 5 thereafter? Yeah, you can. Okay, so there's no reason to get rid of this guy. How about 1 to 1? Yep, there's a lip, and then you can go from where? 1 to 5 eventually. Yeah, there's a way to do that. So those two terms look like they're there. And what about this one? 1 to 0, is that possible? Yes, that's possible. But from 0, can you get to 5? Sure. Okay, so sadly, it looks like everything else is possible here. Okay. So let's write it all out. Row 1, 5, I don't know yet. The probability of going from 1 to 5 immediately, that's not possible. 1 to 5 in one step you can't do. So that one's 0. Okay. Now let's see what these are. What's the probability of going from 1 to 0 in one step? 1 to 0 in one step is 0.6. And then times row 0, 5. 1 to 1. 1 to 1 is 0.3. And then row 1, 5. And then 1 to 2 in one step. 1 to 2 is 0.1. And then from where 2 to 5, which I think is possible. Yes. Okay, so we have this single equation. And so the idea was to get another equation involving 1, 5, and we've done that. But unfortunately, well, it involves 1, 5 in 2 places. But it also involves 0, 5, which is okay. And it involves this one, which is new. So that's a little bothersome, but we still have 2 equations now. We have this one. And we have this one.
Professor, isn't it okay that we had that last part because we already solved for it?
Yeah, I didn't remember. Thank you. Yeah, so okay. So let's thank you for the good news. So maybe it would be nice to put this on the other side. Row 1, 5, and 0.3, row 1, 5. If you bring this to the other side, it would be 1 minus 0.3, which would be what? 0.7, row 1, 5. And this would be 0.6, row 0, 5. So in other words, I can combine this one and this one. That's what I've done. And then you kindly reminded me that we already know this one. So this has been combined, and this one we should remember 0.1 we already know, but the row 2, 5 we already solved for. So this is a setup. Row 2, 5 was 0.25. One-fourth. So we have this equation, and we have this. And what's the good news? The good news is this is an equation in these 2 variables. This is a second equation in the same 2 variables. Hopefully it's not the same equation. I don't think so. So we have 2 equations and 2 unknowns. We should be able to solve for it. So what we wanted row 0, 5, right? That was the thing we're doing here. Yeah, that was the thing we were asked for. So maybe it would be good enough just to replace different ways to go. Yeah, maybe it's good enough to replace what this one into here and solve for it. I'm trying to see if there's an easier way to go. Yeah, so let's just solve for this one for row 1, 5. So row 1, 5. You can solve for that by dividing everything through by 0.7. Here's 0.6 divided by 0.7, so that becomes 6/7, row 0.5. And this one becomes 0.1 times 0.25 divided by what? 0.7. So here we have an expression for row 1.5. And I'm thinking we can then just put that into here and get this thing. So why don't we do that? We can do the arithmetic if we want, or we can just wait, doesn't matter. So what do we have? Row 0.5. Row 0.5 from our first equation was 0.6 times what? Row 1.5. But row 1.5 is all of this stuff. So that's 6/7, row 0.5 plus 0.1, 5, 7. Okay, so we have all of this, and we should be able to solve for row 0.5. So what do we have? It's row 0.5 equals, I guess this we don't like fractions mixed with decimals, but it's not a big deal. So I'll just leave it as this equals 0.6 times 6/7.
Professor, I worked out the numbers if you want those instead.
Hang on one second, but I probably will take that kind offer.
Okay.
I'm just trying to show the steps for those who might need it. Okay, so multiplying this by this gives us this, and this is some 0.6 times all of this stuff. And then all I would do next is now I have one equation, one unknown, right? So I would bring this to the other side. So it'd be row 0.5 minus 0.6 times 6/7. 0.5, and that equals all of this stuff. Okay, I did it right. 0.6, 0.1, 0.25, all of 0.7. And from here, you can just factor out the row 0.5. And what's left is 1 minus 0.6 times what? 6/7. Here is this again. And so now you're done just by doing what? Row 0.5 would be equal to 0.6, 0.1, 0.25, 0.7, and divide by whatever this is, 1 minus 0.6 times 6/7. And what's your final answer?
I got 0.044.
0.044, and that's it, or does it keep going?
I did a little bit of rounding,
Okay,
so it keeps going.
okay, so the truth is, let me see, yeah, it's going to be nasty in a way because we got 6/7 here, and that has like a repeating decimal block of 8 digits, 6 digits long. But I think this is, so let's call this approximate, right? The point is what? And the point is, when we tried to find row 0.5 directly from 9b, it looked pretty innocent. It looked like, gee, we've got one equation and two unknowns. And this is the one we're after. So I used 9b to develop a second equation for this guy. And that didn't look so nice at first, but the more I looked at it, some of the terms were zero, 3 of them in particular. So it's sort of key to recognize the zeros when they occur, which I did. But what I didn't remember is that I had already done this one. So I got help in that score. Knowing that this was already done allowed me to put this number. So now we just have this equation. Two variables are the same as the two variables here. So these two, I'll put little asterisks next to them. This equation and this equation is where you start to see the light at the end of the tunnel, because you have two linear equations and two unknowns. So you should be able to solve for them. And I sort of try to do the steps here. Now, clearly you could do the multiplication along the way. I mean, I don't know which is better. Maybe this is better because if it's every time you do a multiplication, you could be introducing an error. So if you're just indicating the products here and then do it all at the end, maybe you're minimizing the chance of it doing an error. Hopefully. But the rest is arithmetic. Once you get the two starred equations here, which are two equations and two unknowns, then it's a matter of solving a system of linear equations. Okay, so this is not such an easy problem, but where are we at? We're done with this. Now, row 1-5, that comes out quickly because you can go back. Now that you know this, you can just solve for this. So you can just go back to this equation and get that. So I think the hard one maybe is this. And it would even be harder if you hadn't done this one first. So there's a little bit of a setup here. Is there any more to this problem, or is this pretty much it?
I think there's a part C. Yeah, I can check really quickly. Sorry.
Yeah, I don't have it in front of me, so I appreciate you doing that. I think this is the kind of problem that you really won't be able to do this part, the part we just did, from the definition. Why? Because if you're going from 0 to 5 eventually, you can loop here a certain number of steps along the way, and you can loop here a certain number of steps along the way. And so you'd have to, from definition, take into account all those combinations of looping here and looping here. I'm not saying it's impossible, but it's not easy. So this is sort of forcing you to do something else, and 9b is the something else. Is there a part C to this problem or no?
Yes, there is.
What does it say?
Would it be easy for me to just share my screen, or would you want me to read it out?
Try reading it first, and then we'll go from there.
Okay. It says determine a row of 5, 5, and then it says P1 of N5 equals 3. And so sorry.
Oh, okay, we haven't done those yet.
Okay.
Okay, so is it P1 N5 equals 3, something like this?
Yes.
Haven't got there yet, so we have to wait on this one.
Okay. And I think this is another one we haven't got to, but it says E1 of N5.
Same thing.
Okay.
Yeah, so those two, maybe next time, but it did ask for 5, 5.
Yeah, it did ask for 5, 5.
Let's see. Is there any way to do 5, 5? Well, again, if you're going from 5 to 5 eventually, there's all these loops here to consider, but then there's these loops here. So you're basically going this way, you'll never get anywhere, but this way you can come back. I think I would just do the 9b again. Let me see how it would look. So 9b for 5, 5, row 5, 5 would be getting from 5 to 5 in one step. That'll be a loop. Plus the probability, plus a sum. And how does the sum look? all the places z not equal to 5, such that you're going from 5 to z in one step, and then you're going from there to back to 5 eventually. Okay, so that's problem 9b again. Okay, so let's write this out. The chance of going from 5 to 5. But take a look at 5 to somewhere else. Okay. If we go 5, from 5, the other places we can go are either 4 or 2. Those are the only two places we can go in one step. And if you go from 5 to 4, you'll never get back to 5. Because these two states, there's nowhere else getting back here. So the only thing from 9b that really survives is going from 5 to 2, which has a probability of 0.3. So the only one that I see surviving this summation is going from 5 to 2, and then going from where? 2 to 5? Because every other possibility, first of all, many of them you can't get from 5 to 0 or 1. And you can get to 3, but then from 3, you can never get back to 5. So the only term that survives of the sum, I think, is this. And how does that look? And well, I'll write it out a little more. The chance of going from 5 back to 5 is just the loop. So that's a 0.4. And this chance is 0.3. So the loop was 0.4, right? Plus 0.3 times the eventual probability of going from where? 2 to 5. Yes. Yeah, so from here, you either go back to 5 immediately, or you go somewhere and then get there from there back here eventually. Okay. And so this is what we have. It's one equation and two unknowns. Do we know either of these? Let's go back to what we just did.
Yes, we know the 2, 5.
Yeah, that was like the first one we did. Okay, so we know the 2, 5 entry. I know the 2, 5, it turned out to be a 4th. So here it is. Okay, so we know that. So this would be just 0.4 plus this, and what did I say, 1/4? Something like this. Then you can simplify it. The rest is arithmetic here. Okay. I think that's all we can do with problem 1. We've done most of it. What's left to worry about in the future will be the remaining parts of 9C, but at this point we haven't talked about that. Any other questions on problem 1 from the sample test? That's a pretty tough first problem. I would say that's maybe a little harder than my usual first problems. And unfortunately, it has a lot of parts. So that's part of what I also, some students don't care for that. So, okay, what was the other one? The other one was to state and prove the Chapman-Kolmogorov equation. So let's at least state it and maybe prove it. So let's flip the page. Add a page. Put some lines on it. Okay. So what it says is this. The statement is easy if you have it memorized. If you don't, then it's not easy. Okay. So there's the statement. Given a Markov chain. The probability of going from state I to state J, say, n steps, m plus n steps, can be done by going from I to K in m steps, and then multiply that by the probability of going from K to J. I lost stuff. J in this many steps. K to J and n steps. And summing up over, it should have been I to K, sorry. K, something in the sample space. So, this could be a finite sum. It could actually be even an infinite sum. So that's the statement. It's the chance of going, where what? I and J and K are all states. This is the state space. And what about M and N? Natural numbers. And this is Chapman-Kolmogorov, sometimes CK for short. Okay, that's the statement. Any questions about that part of the problem? Okay, now the actual proof, which we did I asked you to prove it as well, right? So, yeah, I'm assuming I probably warned the students ahead of time that this was on a list of 5 or 6 things that they needed to know the proofs of. And this would be one. Okay, so they were hopefully prepared. I can't remember, it's 3 years ago or something. But here's the proof. So here's the proof. I think we did it in class, so hopefully I'm doing pretty much what I did in class. If you're going to go from I to J in m plus n steps, this really means you're starting at time 0 at I and at time m plus n, you're at state J. So this is like a conditional probability. You're starting at time 0 at I, and at time m plus n, you're at state J. But you can rewrite this by definition of conditional probability as the probability that at time 0, you're at I, and at time m plus n, you're at J. That's the intersection of these two. And you put it over the condition, which is probability that you started at time 0 at I. And we're assuming this is not 0. Otherwise, it doesn't make sense. Okay. And now what you do is, you started at time 0 at state I, and your time m plus n. I hope you can read that. That's what that says. My ends don't want to look through. Okay. Okay. And the question is, where were you at some intermediate time? In particular, where were you at time m? Well, you could be anywhere. So we can write the top part of this fraction as saying at time 0, you are at I. at time M, you were, had to be somewhere, call it Z. And at time M plus N, you were at J. And then you could have been many places at time M. Where could you have been? Any of the places Z in the state space. So at this intermediate time, you were at some state, and as far as we know, it could be anywhere. And if you add up all these, it's a little bit like adding all the probabilities along a path. And when you sum up over all the Z, you'll get back to this. Because here you're sort of introducing where you were at time M, but you're summing over all those possibilities. You know you had to be somewhere. So each of these have some contribution to this probability. And if you add them all up, you get this. So another way of thinking of it is, this is really the sum rule, because you're taking the union of the probabilities of these three events. And as you vary Z, these events become disjoint. So it's the sum of the probabilities, which is the sum rule for probabilities. Okay. The bottom is still the same. So if you want to justify it, you can say this is the sum rule, which says the probability of the union is the sum of the probabilities. And what we're really saying here is that this event up here, xi, or x0 equaling I, comma, xn plus n equaling j, that event is the union over all Z in state space, x0 equaling I, xm equaling Z, xn plus n equaling j. So there's that, and that's a disjoint union. So the probability of this happening is the sum of the probabilities of these, which is what I'm calling the sum rule. Okay. Now from here, we're almost done. Because this is the intersection of three events. So you write that using the multiplication rule. This is where the review about the rules of probability is sort of important. This would be the probability of the first event, which is this one, times the probability of the second event, which is this one, given the first, times the probability of the third event, given the first two. That's the product rule. And so if we want to go over here, it's the probability of A1 intersection A2 intersection A3. Product rule, multiplication rule, sorry. Would be the probability of the first event times the probability of the second event given the first times the probability of the third event given the first two. So that's what we're using here. So we're using some rules from probabilities. And then you still divide by this thing. Let me see, did I do that one? I messed it up. Somehow this denominator morphed into this. It should have stayed the same. And I only realized it now because I wanted to cancel. And it wasn't going to be there to cancel. So that's how I realized my mistake. Okay, and here's the cancellation I want to do. And now Only at this point does the Markov property come into play. You want to know the probability that at time n plus n, you're at state j, given that you know it's time 0, you're at I, and at time, it should be time m, time m, you're at j. But because it's the Markov property, so by the Markov property, what are we allowed to do? We're allowed to strike the distant past. It doesn't affect the probabilities. All that matters is the most recent time knowledge you have. Okay, and this looks like the summation Z and S. This is going from I to Z in time M. And this is going from J, whoops, that should have been XM is equal to Z, sorry. Let's see if I should have had it above. Yeah, I had it here. I didn't carry it down well. Anyway, XM equals Z, so you're going from Z to J in time N. Z to J in time N. And I think that's it. I hope. Yeah, that's this. Except I made it Z over here. Over here, I made it K, but it's the same thing. Whatever you call the index, you're summing up over all the states where you could be at time N. So it's the same thing. If I wanted to make it more consistent with my statement, then what should I have done? I should have, when I introduced the Z, I should have called it K. And then I'd be summing over K, and then in the end, it would look exactly like this. Okay, does the proof make some sense? The more you see it? Let's recap. It says if you want to get from I to J in this amount of time, n plus n, figure out the probability of going from I to some intermediate state in this state sample space in time m. Multiply that by the probability of going from that state to J in the remaining time. This is the definition of what's on the left side. From here to here is definition of conditional probability. From here to here is the sum rule, where you have to realize that if you, sometimes they call this total probability rule. You can say, where were you at an intermediate time? And it would be the sum of these possibilities. If these sets are disjoint, so the probability of the union would be the sum of the probabilities. That's the sum rule. And then these guys, I lost the index on here somehow. The way I was doing it here was the sum on Z. Let's see if I can do it. And then this is the multiplication rule, where you break this up as 3 events, the probability of the first times the conditional probability of the second given the first times the conditional probability of the third given the first 2. And then use the Markov property to simplify this, and then you rewrite this to be what it is, going from I to Z in time M, and going from what? Z to J in time N. Questions? Cool. Any other questions? Need a little water.
I do have one question, Professor.
Sure.
As we write down these, we go through the proof, would you want us to write down these like little details as well, or can we just write down the equations?
Generally speaking, explanation is worth partial credit. Okay, so especially if you make a mistake. So, so I would say I would encourage the details, right? There's no reason for brevity. Especially since you can get partial credit if you explain things a little more. But I wouldn't write a book. I mean, look what I've done here, product rule. So I think you're asking about these little things, sum rule, product rule, definition of conditional probability, Markov property. I mean, yeah, like if you didn't say the Markov property here, then you're really not, in my mind, fully explaining why this becomes that.
Okay, thank you.
Sure. So I hope I answered that. Yes, include enough details so that you could justify the steps, but don't make it a book. Other questions? Normally I'd look over the sample test, but I don't even know what I did with mine. So is there anything else on the sample test you want to ask about? A little frustrated. I mean, it's all worked out fine because you had the sample test basically. Okay, well, I think I'm going to split then, if that's okay. I'm not hearing anything else, but good questions. I hope it helps it a little further. And we have another tool in our toolkit here in order to find row. Problem 9B is useful. Okay, I'll see you next time.
Wait, Professor, so I was gonna ask about the research group too. What you said, just like send you an email or talk to you about it like a week or two from now, or
Yeah, who's speaking now? I'm sorry.
Ricky, sorry.
Oh yeah, Ricky. Yeah, the problem, normally it meets roughly once a week. And it hasn't been meeting that because I've been involved with